Hi everyone, this is lecture 13 on fixed point methods which are used to solve nonlinear equations. So today our outline looks like we're going to start out and introduce nonlinear equations, and then we're going to jump into these fixed point methods. We're going to start with Picard's method, and then we're going to get to Newton's method. So let's go ahead and start there. So nonlinear equations. So for the last couple lectures we've been talking about linear equations and linear algebra, and today we're moving on to nonlinear algebra. So what is a nonlinear equation? Okay, and I find there's sometimes a little bit of confusion here. So people sort of think of the world sometimes as there's linear equations over here, and then there's nonlinear equations over here, as if they're two separate categories. And really, this isn't two separate categories. This is a single category and then things that are not that category. So I think the way to think about nonlinear equations, if I can draw a little bit better of a circle here, is to say, linear equations, if I take the set of all algebraic equations, linear is this class that we define right here. All right? And then nonlinear is everything that's not that class, right? So linear is there, nonlinear is there, okay? Maybe it'll be better to just draw this arrow down here. Linear is right there, okay? And nonlinear is everything else, all right? So when we talk about methods for solving equations, we have this distinctive class of linear. There's this property of linearity that holds, and that allows us then, because it obeys those certain properties, it allows us to have certain kinds of solutions that are possible. But when we say nonlinear solutions, that means just everything else. And it turns out that for nonlinear equations, what we're going to see is that there aren't general methods for solving them. It's not like you can just solve every nonlinear equation in these direct methods. Okay, so we're going to talk about that in just a second, but I sort of want to point this out at the beginning. So linear is this class. So a nonlinear equation, all right, what is a nonlinear equation? It's sort of tautological, but it's anything that is not linear. Okay? And so I'm not going to go over the property of linearity. You could go back and look at that a little bit earlier in the videos, or you can, and really that's not maybe the scope of this class so much. We want to talk more about numerical things. In this class, you can take a math class where you talk, more formally about the properties of linearity. But typically, there are, in physics-based disciplines, you encounter terms like this. So you encounter polynomial terms. Okay, so these are things like x squareds, x cubes, things like this. All right, and you also often encounter transcendental terms. Transcendental terms. Okay, these are like sine of x, log of x, e to the x, things like this. All right, so these are the sort of hallmarks. If you see x squared, it's nonlinear. Okay, that doesn't obey the property of linearity. All right, nonlinear equations are extremely common in engineering. Okay, I use EQ for equations. Are extremely common. My writing today, suffering. Okay, there's some important things to say about the solvability of a nonlinear equation. So, and I'm going to compare and contrast this with linear. So in linear equations, okay, if you have n equations and n unknowns, you can show that if those equations have certain properties, if they're linearly independent, okay, you can show that you have a unique solution. Right? And again, this is a thing you'll talk about more in, say, a linear algebra class, but that's an important thing to know. Okay? In nonlinear equations, okay, if you have n equations and n unknowns. Okay, you could have 0 solutions, you could have 1 solution, you could have an infinite number of solutions. Okay, you just don't know. You don't know if there's any of these kind of things. So there's no guarantees here. Okay, and this makes them hard. Okay, much harder to solve than a linear equation. There's just, all bets are off. All right, and sometimes this makes students, and especially new students, uncomfortable, to this area because it's a little wide open, and sometimes there isn't a good answer. And from a class standpoint, right, we try and reduce that. If I give you a problem on a test, if there's no answer, you'll have a way to figure that out that we'll have talked about. I'm not going to give you some trick problem just to get you. I'm trying to test you to know the material, not to just get you with some trick. But it's important to know, okay, that this isn't the world of linearity. We're in the real world here in nonlinear case. Okay, so I want to just consider 2 examples real quick to illustrate this point. Okay, so the first one is an example of a kind of nonlinear equation that we'll see all the time, an implicit equation. Okay, and an implicit equation is something like this: cosine of 2 pi x minus x over 3 equals 0. Okay, in this equation, what makes it implicit is that you can't isolate x. Okay, so you can't solve this by hand, so we're going to need a numerical method to go about solving this, right? You can put x on this side, but then there's still an x here. You could take an arc cosine, but then this gets in an arc cosine. There's not a whole lot you can do, right, to get rid of this guy. So, and this equation here, I actually have a plot of it. I'm going to pull it up right here, okay, is this plot right here. And you notice, right, I've got cosine that's causing this wave. And if I want to say, when does cosine of 2x minus x over 3 equals 0, that's where this red line is here. That's 0. All right, and notice that I have one solution there, another solution there, another one there and there, 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 and there. So, I don't know how many that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 solutions. There's 13 solutions to that equation. That's it, though. There's only 13. So that's a little bit crazy, right? 13 solutions. So one equation, one unknown, but there's 13 answers to it. All right? That's a nonlinear equation. Any of those 13 would work, but anything that's not those 13 doesn't work. Okay? So let's look at another example. This one is another one. Here, this is another class. This would be a polynomial. Okay, a straight polynomial. So in this case, we might have something like x squared minus p equals 0, where p is a constant. Okay, and in this case, in polynomials, I'm certain you've encountered this kind of equation before, say in a high school math class. And we know that we have an explicit formula for this, right? So you can use the quadratic formula. And in this case, you have, x is equal to minus b plus or minus the square root of b squared minus 4ac, right, all over 2a. Okay? And so if you go through here, a is equal to 1. That's the coefficient in front of the squared. B is equal to 0, C is equal to minus P, okay, and you can plug this in, and it's actually even easier because we can just solve this one. What we're going to get, hit the erase, x is equal to plus or minus the square root of P. All right, and so you can solve that by hand, but if you have a cubic, there's a formula for that, but it gets harder, okay, and as you get a higher order polynomial, it gets harder and harder, all right, and of course, if I change P, look what happens, all right. So if I have P be a positive number, okay, I can get two solutions. If p is 0, I get exactly one solution, and if p is negative, right, I have no solutions. So in that case, right, even in this really simple case where we've already solved it, depending on what p is, you know, I can have 0, 1, or 2 solutions. All right? So again, nonlinear equations are weird, they're hard. There are certain special cases, like a quadratic equation, that have direct solutions, that have formula, okay? But there are many that don't, and there's nothing we can really do about it. All right, so I'm gonna write that down just to sort of remind us. Okay, so there are special cases. Okay, for example, quadratic polynomial. Okay, with direct solutions. Okay, and when I say direct solution, think back to how we had a direct method, the Gauss elimination formula in the linear case. We had a procedure that we could always follow that would guarantee us an answer. Okay, but there are no general direct methods, okay, for nonlinear equations. Okay, so the entire class of algebraic equations can't just automatically be solved. All right? So the general problem looks like this. So it helps for the general problem to write it in a standard format. Okay? And the standard format that we've chosen is going to look like this. F of x equals 0. So you take all of the equations, okay, and make it equal 0. So this is the equation here. Okay, this is my unknown. Okay, x. And this is sometimes called the standard form. Okay, or also it's sometimes called the residual form. We've seen the word residual before. If you remember when we had a dot x minus b in the case of linear equations and we took the norm, okay, that was supposed to be 0 if we found the solution. All right, so a residual is anything that if you compute it, it should give you 0. So if it's not 0, right, then it's telling you that you're not at the right answer. And so notice here that if we have the right root, okay, if we find, you know, x equals x star, where this is the root, okay, then this should equal 0. And so our residual should go to 0 when we have the root. Okay, so this is sometimes also called residual form, right? And also note this word, the word root, is the special values of x that happen when we're equal 0. Okay, so don't forget standard form. And because I want you to not forget it so much, we're going to do a quick little activity here, and where I want you to write an equation in standard form for me. Okay, so this is a quick activity. I want you to write the following in standard form, okay, where I have the following equation. Log 10 of p is equal to a minus b over t plus c, okay, where I want to solve for t. Okay, so suppose I was given the other quantities, okay, given p, a, b, and c, okay, and I wanted to solve for t. What's the standard form going to be? Okay, so I want you to pause the video for just a second, get out a piece of paper, jot it down, and figure out what the standard form is going to be. All right, so I hope you did that. Okay, so I'm going to show you the standard form. So you can do a couple different things, but the one I sort of always do is I just subtract this side over. So I have minus a plus b over t plus c equals 0. All right, now you could have subtracted this over the other side. so that you get minus log p plus that minus that guy. That's fine. You could have also taken the power of 10 on both sides, and you could have had p minus 10 to the a minus b over t plus c equals 0. Those are all good, okay? Those are all good. Sometimes people do this, though. They say a minus b over t plus c equals 0, because they say, or they might write 10 to the a minus b over t plus c equals 0, because they think when I said f of x equals 0, then they're saying, well, this is p of t equals 0, and then they want to write p equals 0, okay? But that's wrong, okay? Don't do this, don't do that, don't do this, okay? You want to move everything over to be 0. If I solve for where this guy equals 0, I'm finding where the pressure is 0, right? I'm taking the log of that and setting that equal to 0, which would be funky anyway. I don't want to do that, all right? That's a completely different thing than if I know, say, the pressure is, 1 atmosphere, all right? If I know the pressure is 1 atmosphere, then that's going to give me a different answer. So you want to move everything over, okay, and set that equal to 0. So that's the standard form, all right? So I think this is the hardest part about this, is making sure you get the standard form right. I don't think that's that hard. I think that's the trickiest thing maybe that messes people up. Okay, so that is the first part. Let's go to the second part. Fixed point methods. All right, let me get a new page while we're at it. All right, so now hopefully I haven't discouraged you too much. I said that there are no general direct methods. Okay, and what I said, a direct method was something like the quadratic formula, okay, or Gauss elimination, right? Those were examples of direct methods that we've seen. But the important thing is there are, specific cases where there are direct methods, but no general direct methods for nonlinear equations. Okay, so no general direct methods for nonlinear equations. So what are we going to do? We need something that's not a direct method. We are going to have what's called an iterative method. So instead, we have iterative methods. Okay, and an iterative method you can think about as like a guess and a check. Guess and check, okay, and then repeat. All right, so you make a guess, you check if it's right, then you update it to a better guess, and then you check that one, and you update it to a better guess, and then a better guess, etc., until you hopefully converge to the right answer. Okay, so then you repeat until we say we converge. Okay, and by converge we mean it stops changing. Okay, and we get to the right answer. All right, so and one class of iterative methods are called fixed point methods. So fixed point methods are a class of iterative methods. Okay, and so what we're going to do in a fixed point method, this is the generic strategy. So here is the general strategy, right here. General strategy. We're going to take f of x equals 0, all right, and we're going to rewrite it in a new way. We're going to rewrite it as x equals g of x. Okay, so there are different ways to do this. That's why it's a class of methods. All right, there's different versions of fixed point methods because there's different ways to write this x equals g of x, as we'll see in a second. Okay, but we rewrite it as x equals g of x. Okay, and then we do this. Then we guess a beginning x, x0. All right, we take x0 and we plug it in, and we calculate g of x0. Okay? And we use g of x0 gives us a new x, which is x1. Great. Now we can take x1 down here, and we use x1. I'm actually going to put an arrow here. Let me do this to give us x1. Okay? Then we use x1 to compute g of x1, which will then give us x2, which we use to compute g of x2, and on and on and on, all right, until finally we get to a point where at some xk plus 1, we have that equals exactly g of xk. Okay? And once they're equal, it doesn't matter if I calculate it and plug it in again. Okay? It's at a fixed point. Okay? X is at a fixed point. Okay? It does not change. Okay? So if you were to plot, x versus k, right? It might change, and then it would come to a spot where it would just be the exact same number, all right, the whole time. It gets fixed, all right? So that's why it's a fixed point. So we will call that x star is equal to g of x star, okay, because now they're the same thing. So x star is this fixed point here. So this would be x star, all right? That equals x star right there. That's x, that's at a fixed point. Okay, and that is now a root. Okay, because if that is true, then we rewrote that up there, and what we can say now is that f of x star equals 0, so x star is a root. Okay, so that is the strategy behind a fixed point method, but I haven't told you how we do this rewriting process. Okay, so I'm going to do that in just a second. So I'm just going to make a note. So how do we pick g of x? Okay, how do we do that? There's going to be two ways we're going to do it. One, we're going to call Picard's method. That's one way of picking g. Another way is Newton's method. Okay, and we're going to get to that in a second. But before we do, okay, we're going to take a little detour. Okay, so hold that thought for a minute, and we're going to do a detour. And what I want to show you is an example first of pseudocode for a fixed point method. Okay, so it turns out this pseudocode is going to be good for both of these, but I want to put that on hold for a second, and I want to show you this pseudocode for a fixed point method first. Okay, so let's think about that. How am I going to code this process here, where I have a guess, and then I use a function, and then I update my guess and a function, etc. Let's write that code out. Okay, what do you think is going to do? What do you think is going to happen? What does that look like? What happens when we have something where we're counting and the numbers are increasing? All right, that should be sending off warning signs in your brain that loops are coming. Okay, because we're going to use a loop here. All right, so how do we do it? So we first start off and we say x is equal to some guess value. All right, this might be 7 or something like that. All right, and we're going to define a couple of numbers that you'll see will be useful in a second. We're going to define a tolerance here. Maybe it's 1e to the minus 8. Okay, that is 10 to the minus 8, right? Convenient way to write that in Python. We're going to have a counter k, which we're going to start at 0, and we're going to calculate a residual, which is going to be the absolute value of f of x. Okay, so remember this is the residual. Okay, it equals 0 when at the root, right? So here I can evaluate my function. So assume that f of x is defined somewhere else already. Okay, So if f of x is defined up here, so f of x is defined above, okay, somewhere up there, and g of x is also going to be defined above, right? And so, okay, so now what do I need? I need my loop. Okay, so I'm going to write a loop while the residual is greater than the tolerance. So I'm going to say while this residual here is bigger than 10 to the minus 8, I'm going to stay inside my loop. Okay, so I define the tolerance as this small number, say 10 to the minus 8. And then I use my guess right here, right? So I've used my guess to evaluate it. So if I already know the answer, I don't even have to do my while loop. But presumably my guess isn't that close, right? It's not so close that I've got within 10 to the minus 8 of the value of the function, okay? So then what do I do inside my loop? I'm going to come down here to be inside the loop. So I say x now is equal to g of x. So this x, right, this is where the x that's assigned here goes. It comes in first, and then it gets assigned to x. Great. Perfect. Okay? And then I just make k, I increment it. I say k plus equals 1. All right? And then I need to calculate the residual again. So I say the residual is equal to the absolute value of f of x. Okay? Because I need to check if I'm done or not. And that's it. So the residual then comes up, I calculate this, I go back, I evaluate my while loop. Oh, forgot a colon here. Evaluate my while loop. Is the residual greater than the tolerance? Yes, it still is. Update x again. Update k. Calculate a residual. Come back, do it again. Again and again and again. Around it goes. Okay? Until I either converge. Okay, so when am I going to converge? So when, right, f of x approaches 0, then I'm going to stop and I'm going to get out of here. Okay? So that, that's how I'm going to know that I've converged to my solution. Okay? This will quit. Okay? This will, we say that will converge. Or has converged. Okay? All right. So that's a quick example of the pseudocode. So let's go back now and think about how do I go about getting g of x? How do I pick this? What are the different strategies for doing that? Okay. So now we're on how to pick the g of x. So the first one is Picard's method. Okay, so Picard's method is probably the one that you were thinking of when I did this. All right, so in Picard's method, we simply add x to both sides. Right? Did you think of that one? I thought of that one, I think, the first time I ever saw this. So I take f of x equals 0, okay? And I just add x to both sides. So I do x plus f of x equals x. And now I call this guy g of x. Okay? So in this one, g of x is just defined as x plus f of x. Okay? And now I have my fixed point method, right? I've got, and I can write this now as an iterative formula. I can write x as k plus 1 is equal to, x plus f of x. So x at k plus f of x, at k. All right? So think, if I have this guy right here, x equals g of x, I might not even need to define a whole g of x function. I could just write x is assigned to x plus f of x. All right? And I've got that guy right there. Okay? So that is Picard's method. Right there. All right? So the takeaway from this, what we'll see, okay, is that Picard's method is easy. Okay? It's very easy to write down, okay, but it's not reliable, is what we'll see. Okay? So it doesn't always converge. All right? So let's look at a different method then. If this one's easy but not very reliable, let's think about another method. And this method is called Newton's method. Okay? And in Newton's method, Newton did something a little bit more subtle. Newton said, I'm going to do this pictorially. Okay? Newton said, and this is the Newton, by the way, that we're thinking about. He said, we're going to start out with a guess, the same way that we had a guess, previously. And what I'm going to do with this guess is I'm going to draw a line tangent to my function. So there, we drew a line tangent to that function. And if I draw a line tangent, then I can follow that line all the way to where it's equal to 0. Okay? And if I follow that all the way till it's equal to 0, that's right there. And there's a formula that will do that. That if I take the tangent line, okay, and then I set it equal to 0, so I find the tangent line and I set it equal to 0, and that gives me that point right there. And that's the formula that tells me what it is. Okay? And if I take that point, now I can find the tangent line where, at that point on the function, find the new tangent line and trace that one to 0. Okay, boom, trace it to 0 there. Now I can take the next tangent line from that new spot, trace it to where it is equal to 0. It'll give me a new point where it crosses. Trace that one, trace that where it's equal to 0, and hopefully you see where it's going. Okay, it found the root. All right, if I keep following all these tangent lines, it gives me the root. Okay, Newton was pretty bright. Okay, and so the key to this one then is knowing that formula, okay, that will give you the next value, right? So it was showing you what it is. It's like, how can I find what the tangent line is? And I'm not going to do the derivation for you, so it's not that hard, but the derivation is in my online notes. Okay, you can check them out. They're there to look at. It's a pretty easy formula. It just involves a Taylor series. Ooh. Okay, it's pretty easy to follow, hopefully, but I just don't want to take the extra time here now. But essentially, what that gives us is a g of x that looks like x minus f of x divided by f prime of x. Okay, so the derivation gives us that guy, and that's what gives us that method. Okay, and so then you can write down, if we follow the same pattern here, as I scroll up to look at x at k plus 1 is equal to g of x at k, all right, I can write down x at k plus 1 is equal to x at k minus f of x at k divided by f prime of x at k. Okay, and this f prime here, I neglected to say that, that in the denominator there, okay, that's the derivative. Okay, so that's df dx, the first derivative of f with respect to x. All right, so this is Newton's method right here. Okay, so different g of x. It's the g of x designed to get us the tangent line. Okay, so it's the tangent line, find the 0 of that one. Okay, so this guy, Newton's method, is a little harder than Picard's method. Okay, why is it harder? Well, you have to take the derivative. Okay, you have to find that derivative for yourself, and it's a little bit harder. You have to divide. Okay, it's not that much harder, but it's a little harder. But it's way more reliable than Picard's method. Like, way more reliable. Okay? Now, it doesn't always work, but it works a lot of the time. Okay? One of the ways it breaks is if, when does it break? Okay, it can break for a couple different reasons, all right? But mostly it breaks when the denominator here goes to 0. Okay, if I have something where my derivative goes to 0, and think about where that is. That's at like local minima and local maxima, right? If I get one of those in here, that's going to give me a problem, right? That's going to send me shooting off to infinity to try and find my answer. Okay, so that's when this guy breaks. But other than that, it's pretty good. You know, if you just watched that last example we had here, right? I wasn't very close to the root when I started. Let me go all the way around, okay? Right, I guessed pretty far away from the root, and it got me within only 5 steps. It got me pretty darn close, right? So it's pretty good. It's a pretty good method. So let's do a quick example of Newton's method. Turns out that you can do Newton's method by hand, right? So sometimes maybe if you're in a class and you have to find the solution to some nonlinear equation, and say, heaven forbid, you couldn't remember, you know, how to, you know, what the quadratic formula was or something. I mean, you should always remember that one, but if you couldn't, you could also just do Newton's method, and within a few clicks, you could figure it out. Okay, so let's do an example. Let's do exactly that. Let's solve for x squared equals 4 with Newton's method. Okay, suppose you don't have a calculator and maybe this is like 5, and so you can't take the square root of 5. Maybe that would be a real pain. So maybe you try and use Newton's method. I don't know if that's a good reason or not. We know what the answer is going to be here, though, right? We know that the answer should be plus or minus 2. All right. So what we need to do Newton's method is we need to write down f of x in standard form. Okay. Remember that this f of x is in standard form. So f of x here is going to be what? It's x squared minus 4 equals 0. Standard form. Okay, don't forget to do that. Don't write x squared. If you forget the 4, right, you're solving for where x is squared is equal to 0, and you're going to get 0. Make sure you include the 4. Then we also need f prime of x. We need to take the derivative. Okay, even I can do this derivative. That's 2x. All right, and so now we can write down Newton's method's formula. X squared k plus 1 is equal to x at k, okay, minus, don't forget the minus sign. That's the other thing that people always screw up, is they forget the minus sign. Okay, you write f of x of k, so f of x up here, that's x of k squared minus 4, divided by f prime, which is 2x at k. All right, so now we can make ourselves a little table, right? That's our Newton's method formula. Let's make ourselves a little table here. Let's make a table of k. Let's make x of k. All right? And then over here, let's make g of x, which is this thing here, right there. So we're going to have g of x of k. All right? So at k0, we have to start off with a guess. So I'm just going to guess 1. Right? We know what the answer is, so we know this is a little silly, but I'm going to guess 1 because it's what's in my notes. Then we have to evaluate g of x of k. So we put in 1 in here. So we get 1 squared minus 4. That's negative 3, right? And then we have 2 times 1 down here. So negative 3 divided by 2 is a negative 3 halves. And a negative 1 there is a 3 halves. And then this is a 1. So 1 plus 3 halves gives us 5 halves. All right? Now we go, what do we do in this? We take the g of x, which we found over here, and we set it equal to that one. So we know that this one is going to be 5 halves. Okay, so we're now on k1. That's 5 halves. We take 5 halves and we plug it in here. Okay, and now if you go ahead and punch that into your calculator or something, you're going to find that, 5 halves squared. I'm not going to do this all out. You're going to find that this is equal to 2.05. Okay, so pretty close to 2. Now where does that go? That one, right, this one came down here. That one's going to go down here. It's going to be 2.05 because we're going to take all of that and assign it to the next k at 2. Now I take 2.05 and I plug it in there, there, and there. And what do I get out? I'm going to get out 2.00060, or like 1, basically. Okay? So now I'm very close to 2, which I know is my answer. All right, so if I do just one more, now I have 2.00061. Okay, I plug that in, and now I get 2.00000, okay, up to like at least 7 digits. Okay, so within only 3 iterations really. My first guess was there. I was already 2.5 here, and now I'm getting there extremely quickly. Okay, so I want you to take a second, and practice on your own. So do a little activity real quick. Okay, pull out a piece of paper, or that piece of paper you have from earlier, and I want you to solve for e to the x is equal to 2 using Newton's method. Okay, start with a guess also where you have x at 0 is equal to 1. Okay, you know what the answer should be. The answer is going to be the following. I don't want to put an equal sign. The answer is going to be x is equal to log of 2, natural log of 2, which is 0.6931. All right? So you know that that's what it should be, but follow this same procedure. Take the, standard form, take the derivatives, make a little table, see if you can't get that to go. All right? Okay. So I'm not going to rework out that whole example, this whole example for you. I hope this was useful. But let me just sort of summarize where we've been. Okay, we've come to the end of the lecture here. So let's go back and think about what we did. So we said, let's talk about nonlinear equations. And we said nonlinear equations, they're equations that aren't linear, right? There's no general direct method for solving them. So instead we said, and we said there were different kinds. We said they could have, that they were harder, that they could have an infinite number of solutions, they could have 13 solutions, they could have 0 solutions. It just depends, all right? And so there's no general direct way to solve them, so we had to come up with an iterative way, or a guess and check way. And so we talked about this class of methods called fixed point methods, and in these fixed point methods, right, we come up with some way in which we guess something, and then we calculate it, and then it gives us a closer answer. And then we can take that thing that was closer and put it back in, and it gets us a little closer. And by getting closer and closer and closer, we asymptotically approach the right answer, and hopefully we converge and get there. And we said there were 2 different ways that we learned to, of what formula to plug in. One was this easy one where we just add x to both sides. We call that Picard's method. It doesn't always work, but it sometimes does, and it's pretty easy, so why not? We said a better way was Newton's method, where we took a tangent line and predicted where we should be. And that gave us a formula that came from a Taylor series that I sort of glossed over, but I said is in the notes if you want to look up how to derive it. And then we practiced doing that. All right? So this concludes our lecture on fixed point methods. I have another example video that I'll post that goes over how to program them. Although we saw a little bit of some pseudocode about how to code these, and you could probably figure it out on your own from here if you don't want to go watch that video. But with that, I'll close the video and say thanks for watching.